I will now talk about two very important operations that we apply to functions. One is the inverse. We invert a function. The other one is the compositions of two functions. Okay. Now, the inversion of a function is applicable in very, very specific case. So suppose we have a function from a to b that is a bijection. So it's one-to-one and onto. Then the inverse of the function, which we we denote by f to the negative 1, is a function now from b to a, right? We inverted it from b to a, defined by f to the negative 1 of b to be a if f of a equals b. So if we have, for example, this function here, this function, so suppose I have this is a and this is b, and this is the function f, then the inverse of this is the following function. So if this is b and this is a, the inverse is this. Okay, so look what happened here. So if this element here is a and this is 1, f of a is 1. In this case here, this is the f to the negative 1. F to the negative 1 of 1 is a, right? So this is 1 and this is a. And if this is b, c, and this is 2, 3, we have f of b equal 3, and f to the negative 1 of 3 is b, and f of c is 2, then f minus 1 of 2 is c. Okay, so this is the inverse of a function. And again, for the inverse to exist, the function has to be one-to-one and onto. And think about it carefully why that is the case. If the function is not one-to-one, it means that we have two elements in A that we map to B, to a same element in B. But then if you try to inverse, then we have a function that's mapping one element to two different elements. That's not a function. If it's not onto, then there is an element in B to which we map nothing. And in that case, the function is not defined on something like that, okay? So if I want to illustrate this diagrammatically here, so let me erase this. So, and let me draw a function that's not one-to-one. So if I have this function, for example, this is not one-to-one, so I have an element here, two elements that map to the same thing. Let's call them A and B, and this is 1. If this is f, then what we are saying is that f to the minus 1 of 1 is A, and f to the minus 1 of 1 is B. But this is problematic. This is not a definition of a function. Notice that the inverse is a function. It has to be a function. And here we are mapping the same element, which is 1, to two different elements. This violates the definition of a function. If we look at a function that is not onto, so imagine that I have this set here, and I have a function that is not onto. So this is a function that's not onto, and suppose this is 1 and 2, and I want to look at the inverse, and I ask what's the value of f to the minus 1 of 2. It's not defined, right? Because nothing was mapped to it. Therefore, this is not a function. This is why we need for the function f to be both one-to-one and onto for us to be able to define the inverse of that function. Okay. In general, if you want to think about it, how do we represent this, or how do we write this clearly for general functions? So imagine that we have the function f of x plus 1, which we had talked about before. Then the inverse of this, I am mapping y to y minus 1, right? So if we want to go back from the image to the source, and f to minus 1 of y is y minus 1. This is the definition of an inverse. The second operation I want to talk about is the composition of functions, which is different from the product or multiplication of function. And notice the symbol here is different. This is not f times g, it's f this small circle g. So the composition of function has to be applicable to functions on different, not necessarily different, but have to satisfy the following property. If f is from b to c, and g is from a to b, then we can compose f on top of g. So we apply g first, So G in this case, so we have A, we have B, and we have C here. So G is mapping A to B, something like this. Okay, so this is G. And F is mapping B to C. So F composed with G on the element A is basically you first apply G to A, and this takes you now to an element in the set B, and then you apply F to G of A, and this takes you now to an element in C. This is why F of G, this set is from A to C. It's a function from A to C. Okay, so if we want to look at specific example here, let's look for example at f of x, let's say 2x plus 3, and g of x is, let's say, 3x plus 2. And I say, what is f composition with g of x? Well, the composition of f with g is basically f of g of x. So this is f of 3x plus 2. And then we plug 3x plus 2 in place of x in f of x. So this becomes 2 times 3x plus 2 plus 3, which is 6x plus 4 plus 3. So 6x plus 7. Yeah, this becomes. Okay, so this is the notion of a composition of functions. Notice that the composition has order, right? So if I compose f on top of g, so f of g, it could give me one result. G of f could give me a different result, okay? Unless the two functions, for example, are the same, and so on. So this is the composition of functions.